In this video, we are going to talk about the pH of weak acids and bases. But before we come to the pH of weak acids and bases, let's first remind ourselves of the things we already know. We know that we have strong acids and strong bases. So for example, if HA is an acid and then we put it in water, H2O. So this is in the aqueous phase and then this is a liquid. We know that it will dissociate completely because it's a strong acid into the A- anions, which is in the aqueous phase, then plus the hydronium ions. So finding the concentration of the hydronium ions, we can find the pH by saying that pH is equal to minus log of the concentration of the hydronium ions. It is the same thing when we come to bases. So for example, if we have a base of this form BOH in aqueous phase and then we put it in water, then it will undergo complete dissociation. So if you undergo complete dissociation, we will have the B- in aqueous phase, then plus the hydroxide anions also in aqueous phase. And then in this case we can calculate pOH because BOH is a strong base. So pOH is equal to minus log of the concentration of the OH anions. Now, from theory, we know that pH plus pOH is equal to 14. Contrary to the concept of strong acids and strong bases, weak acids and weak bases do not undergo complete dissociation. So for example, if we have HA, said that HA is a weak acid, then instead of it undergoing complete dissociation, so HA in aqueous media, and then when we put it in water, it will undergo a reversible reaction to give us the A anions and then the hydronium ions. And this means that both the forward reaction and then the backward reaction continues indefinitely, and we can still find the pH by finding the concentration of the hydronium ions. The factor that determines whether an acid is strong or weak, or whether a base is strong or weak, is dependent on the Ka, which is also known as the acid dissociation constant, or Kb, the base dissociation constant. The strength of an acid increases with an increasing Ka, or the strength of a base also increases with an increasing Kb. On the contrary, we also have the pKa, and then we have the pKb, and then the pKa is equal to minus log of Ka, and then pKb is also equal to minus log of Kb. Whilst the strength of an acid increases with an increasing Ka, or the strength of a base increases with an increasing Kb, on the contrary, the strength of an acid decreases with an increasing pKa, and the strength of a base decreases with an increasing pKb. So in other words, it is inverse in the case of pKa and then pKb. But then Ka times Kb is equal to Kw, where Kw is the water dissociation constant, and also pKa plus pKb is equal to 14. Now, how do we write the Ka? Acid dissociation constant is equal to the product of the concentration of the product, then divided by the concentration of the reactant. So in the case of this equation, then Ka is equal to concentration of the A- ions, then times the concentration of the hydronium ions, divided by concentration of HA in aqueous solution. Nonetheless, for liquids and solids, we don't add them in the writing of the Ka or Kb. And it is the same idea when we come to Kb. So having understood this, then let's take some examples and then explore this concept. What is the pH of 0.5 molar solution of ethanoic acid? Ka of ethanoic acid is 1.8 times 10 exponent minus 5. So let's write it here. We need to first write an equation involving the dissociation of ethanoic acid in water. So aqueous ethanoic acid, then when we add it to water, H2O, which is a liquid, it would undergo a reversible reaction because ethanoic acid is a weak acid to give us the ethanoate anion and then plus hydronium ions, H3O plus in aqueous solution. Now, for the initial concentration, you see that we're given 0.5 molar of ethanoic acid. So this one is 0.5. This is the initial concentration. That means that it has not yet undergone any dissociation. And for that matter, the ethanoate anion is 0 molar and then the hydronium ion is also 0 molar. Now, we also have the change. When it starts undergoing dissociation, some of the ethanoic acid will be depleting. So because it's depleting, that sum we are representing it by X, and it is negative X because it's depleting. But it will be depleting into the ethanoate anion and hydronium. So here will be plus X and here will also be plus X. Then we have the equilibrium concentration. In the equilibrium concentration, we just need to add the initial concentration to the change. So in this case, for the ethanoic acid, is 0.5 minus X. And then here is 0 plus X is X. And then here to 0 plus X is X. So the next thing we need to do is to write the Ka. We know that Ka is equal to the product of the concentration of the product. So that will give us concentration of the ethanoate anion, then times the concentration of the hydronium ion, then divided by the concentration of the ethanoic acid. So now we're giving Ka to be 1.8 times 10 exponent minus 5, and this is equal to the concentration of the ethanoate anion is X and concentration of the hydronium ion is X, so times X divided by concentration of the ethanoic acid is 0.5 minus X, so here 0.5 minus X. So this becomes, so let me continue from here. 1.8 times 10 exponent minus 5 is equal to X squared divided by 0.5 minus X. Now, anytime you have K, which is times 10 exponent minus 5 or less than this value, then you can always make this approximation, which is the concentration, the initial concentration of the acid minus the change, approximately equal to the initial concentration of the acid. So in other words, 0.5 minus X is approximately 0.5 because the Ka value or Kb value is times 10 exponent minus 5 or less than that. So what we'll do is that we then say that 1.8 times 10 exponent minus 5 is equal to X squared divided by 0.5. So X is equal to square root of 0.5 times 10, times 1.8 times 10 exponent minus 5. And if you compute this, you are going to get X to be equal to 3 times 10 exponent minus 3 molar. So what it means is that concentration, so let me write it here. concentration of H3O plus ions in solution is equal to 3 times 10 exponent minus 3 molar. So having had this concentration, we can find the pH, because remember we said pH is equal to minus log of the concentration of the hydronium ions. So this is equal to minus log of, into bracket, 3 times 10 exponent minus 3. And if you compute this, you are going to get 2.52. However, we can always verify if this our approximation holds true by using the 5% rule. This 5% rule says that if we take the concentration of X, where X could be either the hydronium ions or the hydroxide ions, and then we divide it by the initial concentration of the acid. So I'm using HA for the initial concentration of the acid, and then we multiply by 100%. This should be less than 5%. So anytime we do this calculation is less than 5%, it means that this our approximation should stand. However, if it is greater than 5%, then the approximation can no more stand. So let's check and see whether our approximation holds. So we got the concentration of the H3O plus as 3 times 10 exponent minus 3. So divided by the initial concentration of the acid, which is 0.5, then times 100%. This is equal to 0.6%. So since 0.6% is less than 5%, it means that this our approximation holds. What is the pH of 0.75 molar HCN solution? Ka of HCN solution is equal to 4.9 times 10 exponent minus 10. So let's first write the equation showing the dissociation of HCN solution in water. So HCN, if we add it to water, H2O, so this is a liquid and this is an aqueous medium. It's a reversible reaction. So we are going to produce the cyanide anions in aqueous solution, then plus the hydronium ions, also in aqueous solution. So I'll use I to represent the initial concentration. So the initial concentration of HCN is 0.75 molar. But before it dissociates, it means that here is 0 and then here is also 0 molar. Then the change, since HCN is depleting, then here is minus X. And since Cn minus is increasing in solution, here is plus X, and then here is also plus X. Then the equilibrium concentration here becomes 0.75 minus X. And here becomes X, and this becomes X. So let's write Ka for HCN. So the Ka is equal to the concentration of the cyanide anions times the concentration of the hydronium ions divided by the concentration of the HCN. So this is equal to concentration of the cyanide ions is X times hydronium ions, which is also X, divided by concentration of the HCN is 0.75 minus X. And then the K was given as 4.9 times 10 exponent minus 10. So this implies that 4.9 times 10 exponent minus 10 is equal to X squared divided by 0.75 minus X. But remember what we said. We said if the K is times 10 exponent minus 5 or less, then we can make the approximation and later check with the percent dissociation and then the 5% rule. So now, this implies that this equation becomes 4.9 times 10 exponent minus 10 is equal to X squared divided by 0.75. So X is equal to square root of 0.75 times 4.9 times 10 exponent minus 10. And if you do this, you get X to be equal to 1.92 times 10 exponent minus 5 molar. So this is the concentration of the hydronium ions. So let me write it here. Concentration of hydronium ions is equal to 1.92 times 10 exponent minus 5 molar. So let's find the pH. pH is equal to minus log of the concentration of the hydronium ions. So pH in this case is equal to minus log of 1.92 times 10 exponent minus 5, and therefore the pH is equal to, if you compute that, you get 4.72 as your final answer. Now let's check whether our approximation is right. So let's use the 5% rule. So now, and that is X divided by the initial concentration of HCN, then times 100%. So the concentration we got as 1.92 times 10 exponent minus 5 divided by the initial concentration, which is 0.75, and then times 100%. And if you compute this, you are going to get 0.003%, and this is far less than the 5%, and therefore this our approximation is true. And we have this question here. It says, what is the pH of 0.25 molar ammonia solution? Kb of ammonia is 1.8 times 10 exponent minus 5. So let's write the dissociation of ammonia in water. So ammonia, NH3 aqueous, when put in water, H2O liquid, it will undergo a reversible reaction. So we are going to form the ammonium ion in solution, then OH minus anion also in aqueous solution. So you can see that because this is a base, or this is a reaction that produces the OH minus anion, then instead of Ka we have to use Kb, which is the base dissociation constant. Initial concentration is 0.25 molar, and then here is 0, and then here is 0. The change here is minus X, here is plus X, and this one too is also plus X. Then the equilibrium concentration, this one is 0.25 minus X, and here's X, and then here's X. So Kb is equal to concentration of ammonium ions times concentration of the hydroxide anions, then divided by the concentration of ammonia. So the Kb is given as 1.8 times 10 exponent minus 5. And this is equal to ammonium ions is X times X divided by ammonia, which is 0.25 minus X. So X squared is equal to, remember that this is 1.8 times 10 exponent minus 5. So it is times 10 exponent minus 5 or less, and therefore we need to do the approximation in this case. So it becomes, so let me rewrite it here. So 1.8 times 10 exponent minus 5 is equal to X squared divided by 0.25. So X is equal to square root of 0.25 times 1.8 times 10 exponent minus 5. So X is equal to, if you compute this on the calculator, you are going to get 2.12 times 10 exponent minus 3 molar. So it implies that concentration of the hydroxide anions is equal to 2.12 times 10 exponent minus 3 molar. Nonetheless, since we have concentration of the hydroxide anions, we can find POH. So POH is equal to minus log of the concentration of the OH anions. So this is equal to minus log of the concentration of the OH anions is 2.12 times 10 exponent minus 3. And if you compute this, we are going to get 2.67. Nonetheless, the question didn't ask for pOH, the question asked for pH. But we know that from theory, pH plus pOH is equal to 14. So what it means is that the pH plus the pOH that we found, which is 2.67, is equal to 14. So pH is equal to 14 minus 2.67. So the pH is equal to 11.33. So using the 5% rule, it's just going to be the 2.12 times 10 exponent minus 3 divided by the concentration of the ammonia, which is 0.25. And this is far less than 5%. So our approximation is true. Calculate the pH and percent ionization of 0.05 molar hydrogen fluoride. K of hydrogen fluoride is 3.5 times 10 exponent minus 4. So let's write dissociation of hydrogen fluoride in water. So HF plus H2O in a reversible reaction will give us the fluoride anions, then plus the hydronium ions. So this is in aqueous medium. This one is also in aqueous medium. This is in liquid. This is in aqueous medium. So the initial concentration of HF is 0.05 molar. And this is 0 and this is 0. The change is here is minus X, here is plus X. This is also plus X. Then the equilibrium concentration, here 0.05 minus X, here is X, and this is X. So Ka is equal to concentration of the fluoride anions times the concentration of the hydronium ions divided by the concentration of the HF. So Ka was given as 3.5 times 10 exponent minus 4. This is equal to fluoride anions is X times hydronium ions is X. So here's X squared divided by 0.05 minus X. However, this is a special case because remember we said for this approximation to be true, we need to use times 10 exponent minus 5 or less. When K is times 10 exponent minus 5 or less, then we can do the approximation. But in this case, it is greater than times 10 exponent minus 5, and therefore the approximation will not hold. So what we need to do is to expand. So X squared is equal to 3.5 times 10 exponent minus 4. All of this times 0.05 minus X. So X squared is equal to 1.75 times 10 exponent minus 5. And then minus 3.5 times 10 exponent minus 4x. So now continuing from where we left off, we established that x squared is equal to 1.75 times 10 exponent minus 5, then minus 3.5 times 10 exponent minus 4x. So let's take everything to the left hand side of the equation. So x squared, and then here becomes plus 3.5 times 10 exponent minus 4x. Then if this one goes, it becomes minus 1.75 times 10 exponent minus 5, and this is equal to 0. So you can see that these equations of the form ax squared plus bx plus c equals 0. So you can see that the quadratic equation, we can use quadratic equation to solve it. So x is equal to minus b plus or minus square root of b squared minus 4ac all over 2a. So x in this case, b squared, sorry, minus b squared is minus 3.5 times 10 exponent minus 4. Then plus or minus square root of b squared, which is 3.5 times 10 exponent minus 4 squared. Then minus 4a, a is 1 times c. C is minus 1.75 times 10 exponent minus 5. All of this divided by 2 times 1. So x is equal to, now we are going to get two values, which is a negative number and a positive number. But because we cannot find the logarithms of negative number, we are only going to write the positive numbers. So x is equal to 4.0 times 10 exponent minus 3 molar. So we got x as equal to 4.0 times 10 exponent minus 3 molar. And x is the concentration of H3O plus. And that is equal to 4.0 times 10 exponent minus 3 molar. So it means that the pH is equal to minus log of H3O plus ions, which is equal to minus log of 4 times 10 exponent minus 3. And if you compute this, we are going to get pH equals to 2.4. The other aspect of the question says we should find the percentage dissociation. So the percentage dissociation is equal to the amount of H3O plus in this system, and that is 4 times 10 exponent minus 3, divided by the original concentration. The original concentration was 0.05 times 100%. And if you compute this is equal to 8%. So you can see that in this case, the 8% is greater than the 5. And that is why we didn't use the approximation, because in this instance, the 5% rule is going to fail. Morphine, which is C17H19NO3, a narcotic used in painkillers, is a weak organic base. If the pH of a 7.0 times 10 exponent minus 4 molar solution of morphine is 9.5, what is the value of Kb? So now we've been given pH. However, let's first write the equation for morphine. So we are dealing with C17H19NO3. If we put this in water under a reversible reaction, the amount of protons will increase. So this will become C17H20NO2 plus the hydroxide anions. So this is plus NO2 plus. This in aqueous solution. This also in aqueous medium. This is liquid. And this also in aqueous. So the initial concentration that was given for morphine is 7 times 10 exponent minus 4 molar. And then here is 0, and this is also 0. The change here is minus x. This is plus x, and this is plus x. And then the equilibrium concentration here is 7 times 10 exponent minus 4 minus x, and here is x, and here is x. Kb of morphine is giving us concentration of C17H20NO2 plus and times the concentration of the hydroxide anion divided by the concentration of C17H19NO3. So Kb is equal to x times x, which is x squared, divided by 7 times 10 exponent minus 4 minus x. But then Kb is what you are looking for. But we're given the pH of the solution. pH is 9.5. So since we are talking about Kb, we are talking about bases, and therefore we know that pH plus pOH is equal to 14. So 9.5 plus pOH is equal to 14. So pOH is equal to 14 minus 9.5, and therefore pOH is equal to 4.5. Now, having gotten pOH, then we can find the concentration of the OH minus ions. Remember that we've established that pOH is equal to minus log of the concentration of the OH minus ions. So it means that concentration of the OH minus ions is equal to the antilog of negative of the pOH. So concentration of the OH minus ions is equal to 10 exponent minus 4.5. Nonetheless, you can see that here the mole ratio here is 1:1. So what it means is that concentration of the OH minus ions is equal to the concentration of the morphine ion, which is the C17H20NO2 plus, and that is equal to 10 exponent minus 4.5 molar. So the unit here is also molar. So Kb is equal to 10 exponent minus 4.5 times 10 exponent minus 4.5 divided by this, which is 7 times 10 exponent minus 4 minus 10 exponent minus 4.5. So if you compute this on a calculator, you find out that Kb is equal to 1.5 times 10 exponent minus 6.